and I promised to send it to you. Unlike the other time, I did not send it because I was somehow very busy. Okay, this time around, we are done with our half-time exam, so we are just marking. So let's look at the first
Okay.
question. You may want to read that.
Okay. Petroleum is a source of many important chemicals. Name two industrial processes which must take place to produce alkenes from petroleum.
Yes.
So, yeah, cracking is one, right?
Say what?
Cracking.
Cracking, yes. Cracking is correct.
And um um yeah, cracking and fractional distillation.
Yes, that's correct. That's correct. Then the next question. Ethene, CH2 double bond CH2, and propene, CH2 double bond CH3 can both be converted into polymers. What type of polymerization takes place when ethene form polymer?
Addition, polymerization.
Yes. Addition polymerization. All right. Next question. What is the empirical formula of the polymer form from ethene?
It's the same, like N CH2, um, like it's the same as the monomer. So it's going to be NCH 2 CH2 C2H4, yes.
What's your answer?
C2 NC C2H4.
Is it CH2 or C2H4?
I said C2H4.
Okay, C2H4. So that is correct.
Like NC2H4.
Okay. C2H4. Okay. Propane has the structural formula of CH2 double bond CH3. Draw two repeat unit of the polymer. I want to give you opportunity to draw that.
Okay.
Or I should do this one, then later when we get there, you can do the other one.
Oh no, I can try this one.
Okay.
Okay.
All right. So the floor is you. I think you can use my yes.
Wait, can I write in structural formula? Does it matter?
And they say just draw. So they didn't give you any way of expressing your answer. So any means of expressing your answer is okay.
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 Right.
You are not supposed to put in the capital bracket.
Oh, okay.
Capital bracket should only be meant for one repeat unit, not two. The capital bracket is to just indicate a repeat unit. Why you draw two repeat units, your bracket can only show. So you can only put the bracket for one repeat unit, and that will give you a correct answer. Nevertheless, so put it for one repeat unit first. Okay. This your diagram has one key leg, and the key leg, I hope you can hear me.
Yes.
Okay, and the key leg is having is that the alkyl group in your diagram, which is your CH3, I mean the yes alkene group, is being shown in your diagram as if it's reacting. The only one that's reacting is the alkene functional group. So this is how you should draw it. Because of next time, you draw this way: CH2 hyphen CH. You bring in the CH3 down like this because it's not part of the reaction, like this. So this is one repeat unit like this. Then you bring in another CH2 hyphen CH, and you bring in CH3 because it's not involved in a reaction. You bring it down like this. So this is your two repeat unit. Your capital bracket surrounds only a repeat unit. While you draw it two times to show two repeat units. So the word two repeat unit, the word two repeat units is showing that the molecule will repeat itself twice, while the capital bracket or then N is indicative of a repeat unit. Why you draw it twice like that? So the CH3 that you have put here is showing that it's part of the reaction. No, the CH3 is not. So you can draw it this way, or you draw it in this way using our popular delta formula like this. So now we are only drawing two repeat units. So I will limit myself to just two repeat units and to be like this. Um, so it continues like this. So it continues in that way. So this is my repeat unit. So this is my repeat unit because this is carbon 1, carbon 2, carbon 3, carbon 1, carbon 2, carbon 3. So you can draw it this way. But since many students don't like this kind of formula, you can go with this one because you can see the CH2, CH3 repeat unit like that. So anyone you choose to draw is acceptable. But you must bring down the CH3 because it's not part of the bonding system. So the CH3 is the one that will help the polymer to maintain a particular strength across. Because the CH3 as it goes, and that CH3 will come again and lie on it. So it will increase the strength of the polymer through van der Waals force. So the CH3 you can also draw it like this. You can also use this manner to draw it. You can draw it this way. So your expression of an answer is very important. How do you give us your answer? You can also do it this way. Hyphen CH2 hyphen CH. Then you put the safety in bracket like this. Then you now continue. Then you say CH2 hyphen CH. Then bring the safety in bracket like this. Then continue like this. In this case, we are telling us that the safety is a branch. It's not part of the bonding system. It does not connect. It's a side chain. Whatever is in bracket is a side chain. And so from here, you can now talk about this one will be your repeat unit, then end down like this. So expressing answers is critical. So I believe that it's okay that is it okay?
Yes, sir.
Okay, good. So we move on to the next one. So C, ethane will react with steam to form ethanol. Propane will react with steam to form two isomers, both of which are alcohol. Suggest the structure of this alcohol. So as a student, I will try and do my propane would be CH3 hyphen CH double bond CH2 plus steam. Then I will have two products according to your Markovnikov rule. Markovnikov's rule says that okay, let me keep quiet. Let's do the answer first before I go to that Markovnikov rule. The hydrogen atom from this water can come to carbon 1. So you have the first product, the first product. If the hydrogen atom comes to carbon 1, we are going to have the first product be CH3, CH bracket OH, and then CH3. That if the hydrogen atom of water comes to carbon 1. If the hydrogen atoms comes to carbon 2, we have the second product, and that will be CH3, CH2, hyphen CH2OH. So we'll be having propan 1-or, propan 1-or, and we have here propan 2-or.
So does that mean that propan 2-ol is the major product?
Yes, because it has two alkyl group that stabilize the intermediate product. I mean the intermediate species. Yes, intermediate species of product. It has two alkyl group that is kind of supplying extra electron to stabilize the positively charged carbon center. So we have that. I hope it's on is clear, Abby.
Yeah, it's fine.
Okay. So the next question, you will do that. Next question. All right. The next question is alkanes and alkanes are both series of hydrocarbons. Alkanes and alkanes are both series of hydrocarbons. Explain the term hydrocarbon.
A hydrocarbon is a compound which contains oxygen and hydrogen only. Oh, sorry, carbon and hydrogen only.
Okay. So what is the difference between these two series of hydrocarbons?
The alkenes have a double bond, carbon to carbon double bond, while alkanes have a single carbon to carbon. bond.
Okay. In other words, alkanes are saturated while alkanes are unsaturated.
I can't hear you. Sorry.
I said, in other words, alkanes are
So I
saturated.
can't.
What do you say? You can't hear me?
I can hear you now.
Uh-huh. But you were saying something now.
Like your microphone, like just now, your microphone goes off and on, like you get low.
Oh, okay. But I can hear you clearly. So I was saying that in
Yeah,
other
but
words,
I can hear you now.
okay. In other words, alkanes are saturated hydrocarbon, while alkanes are unsaturated hydrocarbon. Okay. So there are two marks there. So the word unsaturated in bracket carbon to carbon single bond, while that is for saturated, please. While unsaturated will be carbon to carbon, at least one double bond. So you include the word saturated for alkane and unsaturated for alkene. And while you include the word, you put in bracket carbon to carbon single bond for saturated and carbon to carbon double bond for unsaturated, because you have two marks there. So we want to hear the word saturated and unsaturated in your answer. The third one, you will see answers as well. Alkanes are simpler alkanes. Sorry, alkanes and simpler alkanes are made from long chain alkanes by cracking. Complete the following equation for the cracking of alkane C20H42. So we have gotten,
Um,
yes,
so it's going to be C8, 16 plus 8, 24. C8, wait, hold on.
so that will be what?
C8, C8, H18.
H18. So let's find out if it's correct. For the hydrogen, 2 times 8, we have 16. And the other one, 2 times 4, we have 8. That will be 24. 8 plus 6, that's 24 plus 18. That's 42. Okay, that will be 1 mark. That's correct. All right. Okay. Then we have the second one. Alkenes such as butene and ethene are more reactive than alkanes. Alkanes are used in the petrochemical industry to make a range of products which include polymers and alcohol. Dibromoethane is used as a pesticide. Complete the equation for the preparation of or for its preparation from ethane. So what are you going to get here? You tell me the answer and I'll write it down.
So you have C C like then BR, yeah, BR on top.
Okay.
Oh, well, yeah, you have two BRs like left and
Yes.
right.
It can be anywhere. It can be anywhere. So we have 1,2 dibromo. Okay. They say dibromo. They didn't say whether carbon 1 or carbon 2. Just can be anywhere. All right. The next one, you are the one that will also do it. If you got 2. The structural formula of a polyalkane is given below. Polyalkane is given below. Deduce the structural formula of its monomer. I want you to do that. How do you get the monomer?
Mm. I should annotate, right? Okay. It's going to be C H Wait, structure from as in like this in this form. Oh,
They use the
it's
structural formula.
okay.
Yes, you can do that to anyone.
It doesn't matter. Oh, okay. Sorry, I'm trying to draw a bracket.
Okay. All right. I can actually feel your pain during the construction. Okay. Now you are correct. You are 100% correct. I just want to say that to make it easier for you, if they ask you to show the construction in diagram, you are going to do something like this. This one will come here like this, and some will come here like this. And you have like this. So you can do it next time like this yourself, so that to avoid ambiguity like this, they will now turn this one to your structural formula. So you can do like this: CH3, CH, double bond, CH, then CH3. You see that? It does not involve any bracket. There is no, because it's only one CH3, so no need of bracket.
Okay.
Draw it this way. So when you do it this way, first and foremost, like this, you will now bring it up because it's carbon 1, 2, 3, 4. So CH3 still double bond like that. So that there's no any need of, even though they will mark it for you, they will ignore your bracket. It does not involve any bracket. Okay, so that's about that. The next question, um, how is butanol made from butane? Made from butane, say 3, say 2, hyphen, say H, double bond, say H2. Include an equation in your answer. Do you want to try that? How is butanol made from butane? Yes.
Isn't it from like oxidation?
No. Yeah.
No.
When that is what that is a hydration reaction.
Oh,
Hydration. Okay. To save time, is that include an equation. So let's just make it easier. That will be CH3, CH2, CH, um, double bond CH2 plus what? Plus steam to give us butanol. So we are making butan 2-ol. So we have CH3, CH2, CH, OH, CH3. So you put your gas here, and liquid. So they want you to include an equation. How is butanol made from? So it's an hydration process. So you just say it is made through hydration. And you know that it will involve some special condition of temperature, we have about 300 degrees Celsius. It also involves catalyst, which is about concentrated phosphoric acid, and also it involves pressure of 70 atmospheric pressure, 70 atm. It's actually 60 to 70 atm. So you have so the correct condition should be 1 mark, and the correct equation should be 1 mark. But they just say include an equation. So that equation is important. So you prioritize the equation, then you can also write the condition. So with this condition, ethane at 300 is steam. I mean, water at 300 degrees Celsius is going to be steam. And then double bond breaks, and then you can form propan 2 or, I mean, yes, butan 2 or butan 1 or. Butan 1 or is not the major product. So you just focus on the major product. All right. Then cracking changes alkanes into alkene. How could an alkane be converted into an alkane? Include an equation for your reaction. How could alkane be converted? So for example, CH double bond CH2 by reacting hydrogen with it. So you have your CH3, CH3. That's all. That is by what? Hydrogenation reaction. Hydrogenation reaction. And it requires catalyst, platinum catalyst at about 150 degrees Celsius. With the emphasis, you can just write high temperature, but you must mention platinum catalyst. That is hydrogenation. That's an addition reaction, or in bracket, hydrogenation reaction. Okay, number 3. The alkenes are unsaturated hydrocarbon. They form a homologous series, the members of which have the same chemical properties. They undergo addition reaction and are easily oxidized. A, the following hydrocarbons are isomers. So we have 3-methyl, but one, is it but one in 1, 2, 3, 4. 3-methyl, we have 3-methyl, but one in 3-methyl, put one in, and we have here 1, 2, 3, 4, 5. We have 21 in. So they are isomers. Explain why these two hydrocarbons are isomers for 2 marks. Do you want to explain that?
They have the same chemical formula,
Yes.
and they have the
different structural
structures.
formula. So that will give you your 2 marks. All right, the next question. Give the structural formula of another hydrocarbon which is isomeric with the above. So let's go back to the above. Is isomeric with this above. What are you going to draw? It's another structural formula. So we have seen
you can bring down like another side chain.
So bring down the double bond to carbon 2. Okay. So that will be,
Okay.
so you can have CH3, CH2, then CH double bond, CH double bond, then to CH2, like this. So you have pen 2 in to carbon 2, pen 2 in. They are all isomers, like that. So bring into carbon 2, then you have now have structural isomer. They are all structural isomers. The next question, give the structure formula and name of each of the product of the following reaction. The structural formula and name. So we are going to be naming the structural formula 1 and then name of each product of the following reaction. Ethene and bromine. We are going to have.
You can have like 1,
So your
2.
best bet is to write it this way: CH2 so that you can be on the safer side. You will just write your CH2 double bond CH2 plus Br to that. You cannot write this way. Structure formula will now be Br CH2 CH2 Br, like this. So you can have that. Then the name, you now write 1, 2 hyphen
Dibromethane.
dibromo ethane now, not ethane, ethane. So propane and hydrogen. You also save yourself of the headache and write it propane as in CH3, CH double bond, CH2 plus hydrogen. So you now have your answer as CH3, CH2, CH3. The name will be simply propane. So you need to guide yourself very well. There is a place for learning new message and there's a place for writing down the answer. So the writing of the answer is very essential. Third one, put 1 in plus water. Put 1 in. So you're going to write it this way: CH3, CH2, CH double bond CH2 plus water. So in this case, we'll bring in the OH onto carbon 2 as a major product. So you're going to have CH3, CH3, CH2, CH, this way, OH, then CH3, or CH3, CH2, then CH bracket OH, then CH3. Any one of them, or they are both structural formula. And that will be butan 2 or butan hyphen 2 all or 2 hyphen butanol. I like this one, 2 butanol, because I don't have stress at all. 2 butanol. I mean, the OH is on carbon 2, like that. So with that, I will be done and I will just go. The next question, alkenes can be oxidized to carboxylic acid. So we are on oxidation of alkene. And you will be talking here because I want to find out areas of where I can give some correction. And that was the purpose of me planning this class, to include revision, because learning is good, but revision is equally very important. So alkenes can be oxidized to carboxylic acid. For example, Propane will produce ethanoic acid, and methanoic acid. The propane will produce ethanoic acid, CH3-COH, and methanoic acid. Okay. Deduce the formula of the alkenes, which would form the following carboxylic acid when oxidized: ethanoic acid and propanoic acid. Yeah.
Am I supposed to give only one answer?
What do you say?
I don't understand the question. Like, am I supposed to?
Okay. Now,
I'm not sure.
okay, yes, let me explain the question. The question has been structured. Like, we did alkane oxidation. When we did
Yeah.
alkane oxidation, we simply just pick alkane and we oxidize them. But now they are giving you the answer. They're asking you that how can we get these two? From which alkane can these two come from? These two products, ethanoic acid and propanoic acid. Okay.
Would it
For
be like
example, you see,
pentene or something? Oh, hello?
do you get the idea now? Okay.
I can't hear what you're saying, sorry.
Okay, let me do it for you. Let me do it for you. Um, to
I said
obtain
pentene. I asked if it was pentene. That's what I asked.
of what? If it was benzene, is that what you said?
So I can't really hear you.
Okay, because all right. I was saying, okay, I was saying that, did you say pentane?
Yes, that's what I asked if it was that.
Okay, let's find out if it's pentane. Is it pent one in or pent two in?
Um, I'm not really sure.
Okay. We have, how many carbon do we have there? We have ethane and we have propanoic acid. So we're going to have pent two. Let's look at pent two in. O bond, CH, CH2, and CH3. And so when this is oxidized, this one will break into two. So we're going to have CH3, COOH, ethanoic acid, and we're going to have also CH3, CH2, COOH. So we have propanoic acid, ethanoic acid. So this is correct. So look at that. So they're asking you to tell us the alkane. Now, can you give me now the one I will give you only ethanoic acid? Now,
Ethene.
only ethanoic acid. That will be what?
I said ethene.
Ethane.
E- Ethene, yes.
I'm not sure.
Oh,
18 says to double bonds like this one, like this.
yes.
This one will give you carbon dioxide. Give
Oh,
you carbon dioxide, 2 moles of that plus water.
oh, so probably maybe um propene, propene maybe.
Okay, let's try propane. Someone give you, if you break here, C3 COOH plus CO2 plus water. So it's giving you this one and CO2. So it cannot be this one. These are the things that it can give anybody problem. So let's look at this one. Let's look at this one. Both two in, both two in. This one, both two in plus. If you break here, I'm gonna have 2 mole of C3COOH. No any other product like that. So you have 4 oxygen atoms. So you put 4 here. Do you see that?
Yeah.
Can you see the answer now? Both two in.
Oh, yes.
So
Yes.
both two in will give you 2 molecules of ethanoic acid. Only ethanoic acid. I don't think water will be formed because we are having 3 plus 1, 4, 5, 5 plus 3, 8 hydrogen atoms. So we have 6 plus 8. So it will only give you this one. Water is never a byproduct then. So butane will give you only ethanoic acid.
Yeah.
So that is very good. So you revise your alkane oxidation so that when it comes
Okay.
next time, you can grab it. Describe the color change you will observe when alkane is oxidized with acidified potassium manganese 7. What will be color change? The color changing from
Multi-tone colorless.
come again.
Multi-tone and colorless.
It turns from one color to it not
Oh,
colorless.
like purple to colorless.
Yes, purple to colorless. So purple to colorless, yes. So the color change must proceed from the initial acidified chemical form will be purple, then final reaction will be color, going to be decolorized, colorless. And the next question, alkane polymerize to form addition polymer. Draw the structural formula of polycyanoethane. Include at least 2 monomer units. The structural formula of the monomer cyanoethane is given below. So we have your cyanoethane that I called it for one name. I gave you the IPAC name. And I said carbon 1, carbon 2, carbon 3. That
Isn't
would be
it
what?
nitrile? A propyl
Pro
propyl
propane
Oh,
nit
sorry, propane nitrile.
nitrile.
Sorry.
So they are giving you the old name as cyanoethane, CN for cyanoethane. So, so this one can undergo polymerization and here to give us CH-CH2 CH. The CN is not involved like this. So this class is to correct very important point. Then CH hyphen CN. Like this. So I've just drawn 2 repeat units. Then I cannot talk of this one as my N. So I've drawn 2 repeat units. And if you are one who are a specialist and you are perfect, you can do this way. CH2 CH bracket CN, then CH2 CH bracket CN like this. Those who are experts can do it that way, or you just do it the way I have done this way. And so they're asking the structural formula. Okay. So to comply very well, you can do this way. CH2 CH hyphen CN is allowed, then CH2 CH hyphen CN, continue like this. Then you bring in your this N. So you are done with that. So play with this thing very well, and you have polypropylnitrile or polycyanoethane. All right. Let's take the next question. Question number 4. Alkanes are unsaturated hydrocarbons. They form homologous series, the members of which have similar chemical properties. They can easily be oxidized. They can undergo addition reaction. They can undergo polymerization reaction and combustion reaction. 4 major reactions. All the alkanes have the same empirical formula. State their empirical formula. State their empirical formula. Yes.
CnH2n.
Yes. Cn.
H2n.
Okay. Why is the
Right?
empirical formula
Okay.
of the alkane the same?
Because members of the same homologous series share the same and share the same empirical formula, I think. Hello?
You can raise your voice more.
Oh, I said that because they're members of the same homologous series, that's why
Okay.
they share the same.
Okay. Okay. All right. The next question. Alkenes can be oxidized to carboxylic acid by boiling with aqueous potassium manganese 7. Pentoene, CH3, CH2, hyphen CH double bond CH3 oxidizes to CH3, CH2COH, and ethanoic acid. Name these two acids. Name
Um,
these two acids. Yes.
Propanoic acid
And
and ethanoic acid.
that is very easier. Most alkanes oxidize to 2 carboxylic acid. Reduce the formula of an alkane which form only 1 carboxylic acid.
Put two in, which is CH3, CH double bond CH3.
Okay, CH3, CH double bond
CH double
CH,
bond
and
CH3.
then CH. Now they're asking for the formula. Reduce the formula.
Okay.
So you 1, 2, 3, 4. That will be C4. How many hydrogen?
H8.
So many students will write this one, while only few students will write this one. So you must look at the tone of this, just the formula. They didn't say structural, just a formula. The next question. Complete the following equation for the addition reaction of propane. So I'm going to have here CH3 CHBr hyphen CH2Br or CH3 CH bracket Br, then CH2 Br, anyone. With water, this one, you have your CH3, CH bracket OH, then CH3. Draw the structural formula of polypropane. Polypropanes, the structural formula. This one does not have any restriction. Polypropane. So we just know one. You have your hyphen CH2, single bond CH hyphen CH3 like this. And this is polypropane. So the CH3 will come down, or you put it in bracket. Is either like this, also CH2 hyphen CH in bracket CH3, then CH2 hyphen CH in bracket CH3 like that. So this one is two repeat unit like this. So always put down the CH3. It will help you a lot to conserve some marks. Okay. We are almost getting done with the. Let's look at this one. 0.01 mole of alkane needed 2.4 grams of oxygen to complete combustion. For complete combustion, 2.2 grams of carbon dioxide were formed. Determine the following mole ratio. The mole ratio of alkane ratio mole of oxygen ratio mole of carbon dioxide. So we'll do some calculation there. Let me get my calculator. So give me some few seconds to get my calculator. All right, I'm back now. So looking at this, we have 0.1 mole of alkane. We don't know the formula of the alkane, but we are told that we're going to have 2.4 grams of oxygen. So let's look at let's see how we can do it. We have CX H2 N H2N H2N plus oxygen to give us CO2 plus H2O, and a mole of oxygen is 2.4 grams. But we are to the 0.1 mole of alkane. So this is 0.01 mole of alkane. And let's find out 2.4 grams of oxygen. We may not finish everything. So 0.01 mole of alkane needed 2.4 grams of oxygen for complete combustion. So complete combustion. And 2.2 grams of carbon dioxide were formed. That means the following mole ratio. So let's look at that. So 2.2 grams of oxygen, that will be 2.4 divided by 32. So we're going to have 0.075.
That's
0.075.
0.075.
What do you say?
No, I was just saying the answer for 2.4 divided by 32.
Okay. Then the other one, carbon dioxide will be 2.2 over 44. 2.2 divided by 4.
That's 0.05.
Okay. All right. So 0.05. And then that is all of it. Okay. So deduce the mole ratio of that. So I will divide by the smallest one. What's going the smallest one there? That will be
0.01.
so we have 1 ratio this one. So 0.075.
That's 7.5.
What do you get?
7.5.
Okay, so we have a 7.5, and here is what?
5. 5.
Okay, good. So we have 5. So which means that if you remove the 0.5, that will be what? Times 2, we have 10, we have
15.
is that how to remove the 2? 15, then we have 2. So 2 ratio 15 ratio 10. That will be that. Or we can leave it this way for 3 marks. Yes, for 3 marks. All right. So now they're asking us from this ratio, determine the formula of the alkane. From this ratio, determine the formula of alkane. But I know that if alkane is 15,
Oxygen is 15.
What did you say?
I said oxygen is 15.
Yes, yes, yes. I know that that oxygen there should be X plus Y is over 4.
I think
Because so X plus Y over 4 equals to 15. So from there we can get our X. And also carbon dioxide is X. We don't know water, but water, I know that water, H2O, is Y over 2. If you cross multiply this one, we can get X plus, we can get, we cannot cross multiply that now. But we has, the formula of the alkane now, let's look at it carefully. Okay. So this is a stoichiometry. So X plus Y over 4. If you find so we have 4 here. So that will be 4x plus y equals to 15, which means that 4x plus y equals to 60. And having known that, we also know that oxygen, no, okay, we are looking for x. Let's see, x plus y. We also know that which other one now? Y over 2 equals to this 5 is for what? Carbon, right? Okay, carbon.
carbon dioxide.
Okay, it's carbon dioxide. So I know that change. So CO2 is X, and that's 10. So Y, sorry, CO2 is X. So X is 10. So I'm going to put 10 in this equation here. let's look at it this way. Okay, good. So let's put our S here. So we have 40 plus Y. So we have 40 plus Y equals to 60. Therefore, Y will be 60 minus 40. So Y will be 20. So we have gotten our Y to be 20 and our X is 10. So we can have C10 H20. Okay. Let us assess our calculation very well. I'm using the fact that I know that hydrocarbon when they react, we have CX HY plus X plus Y over 4 oxygen. They give me S carbon dioxide plus Y over 2 H2O. So from what they gave me, I got that carbon dioxide is 10. So our X here is 10. And also oxygen, X plus Y, that was 15. So we'll do that. So putting it together from this equation, we get that. I believe we will be correct. C10H20. Okay. C10H20. So if it's another way, I will let you know. But that's about that. So we have here C10H20. C10H20. That's an alkane. Write an equation for the complete combustion of the alkane. C10H20 plus oxygen to give me CO2 plus H2O. So we'll put 10 here and then 20 hydrogen. That will be also be 10. Then oxygen will now be 10 times 2. That will be 20 here plus 10, making it 30. So here will be 15. So C10H20 plus oxygen will give us 10 CO2 like that. Okay. So we get that. Next question. The alkane are a series of unsaturated hydrocarbons. They have the general molecular formula of CXH2N. Deduce the molecular formula of alkane, which has a relative molecular mass of 126. Show your working for 2 marks. You will do that one for us. You have this and you have this. Yes, how do you intend to do that?
So like what you do is that since we know that the molecular formula is equals to the molecular mass, we do like we know the molecular mass of carbon is 12 and the not molecular relative atomic mass of carbon is 12 and that of hydrogen is 1. So you have 12N plus
So
2N equals
12N
to
plus
126. 2N
2N equals to
plus
1.
equals to 126.
Okay.
Then
So we have
that'll be 14N equals to 126. So 126 divided by 14, that's 9. So
okay.
so the molecular formula is C9H18.
Okay. So I'm going to have C what?
C9H18.
Okay, good. So that that? That's correct. The structure formula of propane is drawn below. Draw a diagram to show the arrangement of the valency electron in one molecule of this compound. Use X to represent an electron from the atom of carbon and use O to represent an electron from the atom of hydrogen. Okay, so let's look at how to do that. So let's look at carbon. We have carbon. We also have carbon. We also have carbon. Then we have hydrogen. We have hydrogen. We also have hydrogen, 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 hydrogen. Okay, so we have carbon, 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 hydrogen, 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 and hydrogen. So we're going to have dot, a cross for carbon, done, cross for carbon, done, done. We are doing the simple one, done, done. Then carbon to carbon single bond, cross, cross for carbon. Then carbon to carbon double bond, we have one dot, dot, dot. So we have 4, 4, 8, 4, 4, 8, like that, like that, like that. So bonus mark of, it should be 2 marks or so. We are done. This is O level. I believe so. I think you are clear with this one.
Yes, sir.
Okay. Okay. Draw the structure of the polymer formed from propane. That one you already know already. So, all right. We are done now with this. So I'm going to stop the sharing and look for an analytical chemistry slide. Okay. All right. Can you see my screen?
Yes, sir.
Good. So infrared spectroscopy. Infrared is AS chemistry and is always part of your question, maybe the last question. Yeah, you will see that last question. So the foundation of that is very important. That you can analyze the structure of unknown compound, or you can actually predict through analysis the structure of simple unknown organic compound using IR spectroscopy. Before you start, it will be helpful to know the names and structures of organic functional group. The name and structure of organic functional group. Well, of course, you already know that. Okay, this is alkane, and this is alkyne, like this. And you already also know that hyphen OH, then hyphen C double bond OH, hyphen Cl, hyphen C double bond O, hyphen C double bond H. So let's look at 1, 2, 3, 4, 5, 6, 7. This one is hyphen X. Which one represent? Which of the formula group represent alkanone? Alkanone. Is it 7? Is it 6? Is it 5? 4? Which one? Alkanone.
I think it's 7.
Okay. I'm saying that these are functional groups. Which of them, label 1, 2, 3, 4, 5, 6, 7, represent ketone? Ketone. That's alkanone.
5.
5,
Oh,
4. 4 is let me draw 4 for you very well.
I didn't say 4. I said 5.
5. 5 is aldehyde. 5 is aldehyde. Aldehyde is hyphen CHO. Ketone is hyphen C double bond O, like this. CO as hyphen. So
Wait, alkanone and ketone, they're the same thing.
you cannot do what?
Alkanone and ketone, they're the same thing.
Acetone.
No, I
Acetone.
said alkanone and ketone, are they the same thing?
Yes. Yes.
Oh.
Alkanone and ketone, they are the same thing. While alkanone is IUPAC, ketone is the old name. Aldehyde is the old name, while alkanal is the new name. All right. So we have to familiarize ourselves with this functional group. So number 1 is alkene, 2 alkyne, 3 alcohol, 4 carboxylic acid, 5 alkanal, 6 alkyl halide, 7 alkanone or ketone. Okay. Different covalent bonds have, we are starting now. We are starting. Different covalent bonds have different strength due to the masses of different atoms at either end of the bond. So different covalent bonds have different strength, and that is the truth. Some covalent bonds are stronger than the other. So due to the atoms at both ends, so you will have C to C, and we have Cl to Cl, and you have H to H. Look at that. So they have different strength due to the different atoms at either end. Good. That's 1. 2. As a result, the bond vibrate at different frequencies. So because they have different strength, they will absorb the infrared radiation, and vibration will be different for each of them. So the different way by which they vibrate will help us to know whether it is a particular covalent bond or not, whether it's a single covalent bond or it is hyphen Cl bond or hyphen OH bond, and so on and so forth. So we can know the functional group or the kind of covalent bond that is coming out from such vibration. So they vibrate differently because of the different atoms attached to the different bonds. The frequency of vibration can be found by detecting when the molecules absorb infrared radiation. Various types of vibration are possible. the molecule absorb different amount of frequency due to the strength of the molecule. So a double bond will absorb certain amount of infrared radiation more than a single bond. So the amount that the double bond will absorb will not be the same as a single bond. Okay. So a molecule that has this kind of bond, look at it, will absorb its own unique amount of radiation. So we have a different frequency compared to a molecule that has hyphen OH like this, a polar bond. So they all absorb at own different frequency and alkane. So let's look at let's continue and let's look at first. Let's look at this one. Example includes we have some vibration that we call stretching vibration, stretching vibration, and bending vibration. Look at this stretching vibration. You will see the arrow going down. The arrow going down. So it's like this. The thing is stretching itself up and down, up and down. It's like you hold a rubber band and you can stretch it. So up, down, up and down, up and down. So we have stretching vibration, and it is symmetric. It's symmetric. So symmetric stretching vibration. Then you have the second type of vibration called bending vibration. The molecule, you can see the arrow is kind of the bond is bent is like it's like this, like this. It's like this. Okay. Like this. Look at this way, go this way, and it comes back again. It goes this way, comes back. So bending vibration. The bond is being bending vibration. Then we have the one that goes contrary to each other, stretching vibration. One is going this way, and that one is also going this way, stretching vibration. Look at the arrow, asymmetric vibration. So in this slide, we are learning symmetric vibration. The arrow faces the same direction, symmetric. It's going down together and going up, down, up, down, up, down, up. Bending vibration, bending, making a kind of a curve, while asymmetric, if one goes down, that one will go up, goes down, goes up, goes down, go up. So the same molecule of water can undergo symmetric vibration, bending vibration, or asymmetric vibration. It depends. Okay. Let's look at the next. So you can see this demonstration there. That is symmetric. They are both going down and coming up. That's symmetric vibration. And asymmetric. See that? One going up, the other one going down. Asymmetric vibration. And then we have bending vibration. Look at that. So it's going up and down like that. Bending vibration. Okay. We have some kind of a kind of transmission here.
Sir, can you
Yes.
excuse me for like 2 minutes?
Sorry, come again.
Can you please excuse me for 2 minutes?
The previous slide.
Okay, please excuse me for like 2 minutes.
Okay,
Can I
sure.
be excused for 2
Sure,
minutes?
please, sure. So we have a simple diagram of the infrared radiation device where the source of electromagnetic radiation okay, is passed through the sample. And so you have a reference sample and also another sample that we absorb the IR radiation. So the reference sample and the sample that you're analyzing. So the sample we pass through, we absorb the radiation based on the different bonds inside the molecule which will absorb the radiation and goes to a place. Then we have a recorder, then we have the interpretation of what is being recorded. So a beam of infrared radiation is passed through the sample. A similar beam is passed through this reference sample. So the two of them, the similar beam, the same thing will be passed through the two of them. All right. The frequency of radiation is varied. It is varied to allow the different bond to vibrate. So as the different bond is vibrated, it is being recorded. And this bond will be used for their identification. So bond vibrating with similar frequency absorb the same radiation. The amount of radiation absorbed by the sample is compared with the reference. The results are collected, stored, and plotted. So you'll be analyzing spectral lines. Okay. And it's interesting, it's very interesting. But we'll give you some key to that. So normal molecule, they undergo normal vibration. Every molecule vibrate. Every molecule vibrate. Okay, like this. They can vibrate like this. But once they absorb radiation, their vibration increases. So you have the second diagram. Vibration will increase because of the what? Of the energy that they have absorbed. They have more energy to vibrate. Okay, that's about that one. Then next slide. Identification of a particular bond in a molecule. All right. Let's look at two major bonding functional group. We have OH and we have C double bond O. Some two major bonds that are majorly present in organic molecules, the alcohol and the carbonyl. The carbonyl functional group, you can find it like this in only ketone like this. It absorbs differently. You can find it in alkyl HR. That is aldehyde. Aldehyde. It will also absorb differently. You can also find it in C double bond O O8 as a carboxylic acid. Carboxylic acid, it absorbs differently. You can also find it in C double bond O OR in ester. In ester. So the C double bond O is very important. So you must know the frequency of absorption in ketone. You must know the frequency in aldehyde, in ester, and in carboxylic acid. The same thing goes for the OH bond. You can find the OH bond in alcohol. You can find it also in carboxylic acid. So the OH bond, you'll find it inside alcohol. You also find it inside carboxylic acid. So in carboxylic acid is different, in alcohol is different. It can also be hydrogen bonded. You can find it like this, also having hydrogen bonded to another molecule, maybe like water. So you also note that one. Or to another molecule of alcohol. So it can be as ordinary OH, not hydrogen bonded, in alcohol and as ordinary OH in carboxylic acid, not hydrogen bonded or hydrogen bonded. So you'll be told all of that in the instruction in your question. So the presence of bonds such as OH and CO within a molecule can be confirmed because they have characteristic peak identifiable part of the spectrum. Sometimes you will see it like this. So that is C double bond O. And it can be for ketone, alkana, or carboxylic acid or what? Esters. And then if it is a OH, it can be like this. Let me draw it very well. So it's like this. That is for carbonine. Carbonine. The one is like this. Alcohol. And if it's also very wide like this, it's wider. You can talk about OH in carboxylic acid. In carboxylic acid. But we are not yet there. So the shapes are very important. Okay. Identification of compound by direct. Can you give me just a few minutes, please? Please, I'm coming.
Okay.
Yeah, I'm back. So identification of compounds by direct comparison. The only way to completely identify a compound using IR is to compare its spectrum with a known sample. The part of the spectrum known as the fingerprint region is unique. We have two parts of IR spectrum. We have the fingerprint. The fingerprint region is unique for any compound. Your AS chemistry, they don't bother you about the fingerprint region. So they will put a kind of a borderline that this is fingerprint region. You don't go there. It is unique for every compound. So every compound have their own unique fingerprint region. And that will help you to completely identify the compound. Okay. Just like we have everybody has his own fingerprint. You yourself, myself, we have a different fingerprint and it's unique. If you want to know whether it is Francis or it is Jessica or it's just your fingerprint, it's unique for every molecule and also for every human being. So that area, you don't go to that area. The other area is what we analyze. So there is a gap. The regions are when we get to the spectrum, we will show you the frequency relation between one certain level to certain level that represent the fingerprint and the area that you analyze. Okay. That's about that. Infrared spectra are complex due to the many different vibrations taking place in each molecule. Total characterization of a substance based only on its IR spectrum is almost impossible unless one has a computerized data handling facilities for comparison of the obtained spectrum with one in the memory. It is not totally true that you can actually analyze the compound using only IR. IR is only used for functional group identification. And that was why at the beginning, they ask you that you must familiarize yourself with all the major functional groups, the nitride functional group, the alcohol functional group, ester functional group, carbonyl, and so on and so forth. You see the halide functional group. So you familiarize yourself with the functional group. It's actually only for functional group identification. That's all. And so we have other forms of spectroscopy. We have carbon 13. We have carbon 13 spectroscopy. This one identify the compound using carbon 13. Carbon 13 episode note. Let me not talk about this one. It's not too much. We have NMR. This one uses the environment of hydrogen, like CH3. The environment of hydrogen to identify the structure of a known compound, while carbon 13 uses the environment of the carbon to identify the unknown carbon. So this NMR that use the environment of hydrogen. So when you have a CH, you will know that some CH can have also a CH2, can have a CH3, and so on and so forth. The environment of carbon, of hydrogen, is what NMR uses. And NMR uses what we call the radio frequency range, radio frequency. While carbon 13 is, we also use the radio frequency range, but it uses the carbon, it uses the environment of the carbon to analyze the structure of unknown compound. So carbon 13 NMR and the normal hydrogen NMR combined together with your infrared radiation can help you to completely identify unknown molecule or known compound. So you can not only use the IR radiation alone. It's not enough. So these ones are A2, while IR is just ordinary AS. So for now, we'll limit ourselves with the AS chemistry part of it. Also told. Now, the technique is useful when used in conjunction with other methods. We have the nuclear. I have just explained the nuclear, which is your NMR, nuclear NMR, nuclear magnetic resonance that uses the hydrogen. So you see like it like this. It's a nuclear MR. Then we also have the mass spectroscopy, which is a carbon 13. Mass spectroscopy is also, that one is very, very important and is simpler than NMR, mass spectroscopy. That one, a compound is passed through the mass spectrometer machine, and the compound breaks, it absorbs radiation, and it breaks into pieces. So a compound like this, CH3, CH2, C double bond O, then CH2, CH3. When it can undergo mass spectroscopy and we break into CH3 fragment or CH2, C double bond O, CH2, CH3, it break into different fragments. So the small fragments are obtained, analyzed, and then from there we can find the total structure of the molecule. So we just as we have the NMR, we have the IR, we have the carbon 13, and we have the mass spectroscopy. Okay, so that one is very, that's about 4, NMR, carbon 13, mass spectroscopy, and IR, 4 of them. Now they have brought mass spectroscopy into AS chemistry. They have brought part of it into AS chemistry. So we'll be learning both of them, both the IR and the mass spectroscopy in our AS chemistry. But NMR and carbon 13 are purely A2 chemistry. So we can continue. Okay. So let's look at some things like peak position depend on the bond strength and also the masses of atoms joined by the bond. So for a molecule to absorb an infrared radiation, you consider the strength of the bond and then the masses of the atom joining the bond together. So strong bond and light atoms absorb at lower wavelength. Strong bond and light atom. Weak bond and heavy atoms absorb at high wavelength. Okay, let's continue about what we are doing. So let's look at this, a wavelength in micron. In micron, you have something like this. So let's learn the axis first. We have the label of the axis in percentage. So we have percentage absorbance on our y-axis. So when these molecules, the bonding system, the molecule, when they absorb, the percentage absorbance is calculated, y-axis. And then the frequency, that's wave number, centimeter to power -1 wave number is on your x-axis. So one thing you must know here is the range of absorbance from 4,000 to 400 wave number, from the range of the infrared radiation that will be given the exam is it between 4,000 and 400. But what we are seeing here is between 4,000 and 600. In your past question, it may likely be 4,000 and 400. And so, and in most cases, between 400 to 1,400, you may not need to, this one is your fingerprint region. Fingerprint region. Students doing foundation, they will, there are some functional group here like CCl, this one, carbon chlorine bond, carbon bromine bond. They are in this fingerprint region like this. O H, not OH now, O something. So they are, but the halide, CBr, CCl, they are in their region. So those who are doing foundation, they will ask them to find that one. But your AS chemistry for Cambridge, you don't go to the fingerprint region between 400 and 1,400. But outside the 1,400 to 15, then you start your work. So you begin to analyze. You will see this one like this. That is your carbonyl. That's your carbonyl bond, which is into the carbonyl bond in ketone, like I've just said before. Carbonyl bond in aldehyde, the carbonyl bond in ester, and also the carbonyl bond in carboxylic acid. So that is this one. Is the easiest way to first and foremost understand. That one is the easiest one that you can easily understand. Okay, so we are looking at the graph like this. Like I just said, that from 400 to 1,400, you have no business with that. So your business is this place, like that. Okay, that's about that. Now, let's see the vertical axis absorbance. The stronger the absorbance, the larger the peak. Good. Then horizontal axis, we have the wavelength, wave per centimeter. 1 micron is also 1,000 nanometer. Okay. Let's look at the next slide. All right. Organic molecules have a lot of carbon to carbon and carbon to hydrogen bond within their structure. Of course, that one is true. The spectra obtained will have peak in the range of 1,400 per wave number to 800 wave number range. So this is referred to as the fingerprint. So, like I said to you, that from one like this down, we have no business with that. It is always shown in any spectral diagram or spectrum diagram. It's always shown there. So, and that is the one that helps to know the full structure of the compound because it is unique for the molecule. So we don't go there. But anything above that is what we go. So the fingerprint region 1,400 wave number to 800 wave number. Now the pattern obtained is characteristic of a particular compound, the frequency of any absorption is also affected by the adjoining atom or group atom. Okay. Now, also, the absorption of any functional group can also be affected by the molecule nearby. The molecule nearby. So you'll be seeing this one here, and you'll be seeing something here like this. So that is our CH bond, the CH bond. And the CH bond can be found in alkane, CH bond in alkane, like this, in alkane. In alkane, you will see this way, double bond, like this. So you see that the CH bond in alkane is attached to double bond. So the absorption in alkane and alkane will be different. So the pattern obtained is characteristic of a particular compound. The frequency of any absorption is also affected by the adjoining atoms. So the CH bond is affected by the double bond to C. We also have the CH bond again in alkyne, 1, 2, 3, like this. It's different. It's very, very different because of the ratio. You will see that the CH bond is different because this two bond here, the amount of SP, no, this one, that's SP carbon. When you have this one, we have sp2 carbon, and when you have alkane, you have sp3 carbon, which is sigma bond. So they have different amount of different types of carbon. So it will affect the absorption because they have different strength. I will explain that more later. So, like I was saying, this is a CH bond, CH bond of different molecule. And we have here the carbonyl bond, the molecule, and so on and so forth. But that is just the introduction. Very soon you'll become a master. Now, let's look at this. Looking at this one, you will look at they are showing you the first one now, the carbonyl compound. Carbonyl compounds show a sharp and strong absorption. It is always upside down, like this. This is how you see it in your exam, upside down. So the carbonyl compound shows a sharp, so we have what we call sharp, broad in your data booklet. In those days, we normally use data booklet, but now we don't use it again. They give you, but as you prepare for your exam, you should be using your data booklet. So in the data booklet, I will project that one maybe next class. So that by next class, I will project the data booklet. And then you will see the range of the absorption of the molecule. So this carbonyl compound shows is sharp. So you know the meaning of sharp. When it says sharp now, you can see the end here. The end is sharp, is strong. It is covering the whole of the graph. It's strong absorption between 1,700 wave number and 1,760. So 17 to 1760 wave number. And it's always due to the presence of the carbonyl functional group either in your ketone, aldehyde, esters, and carboxylic acid. Okay, that is that. So you must take note of that. You can find 17 to 1760 for all of them. That is the range. Okay. And then we have another one here. You take note of this one. The alcohol, you look at that, shows a broad absorption between 3,200 wave number and 3,600 wave number. This is just a difference of the OH bond. The OH bond can be from carboxylic acid or from normal alcohol. So 3,002 to 3,600 wave number. And you will see that it is smooth. The curve is smooth, smooth. The one of carboxylic acid is not smooth like this for carboxylic acid. There is a kind of something here like this, then goes like this. The one of carboxylic acid is broader than this one. So you must look at it. When you see the one of alcohol, you should be able to identify it's very smooth. So it's broad. That is talking about it's like this broad, but the OH from carboxylic acid is broader than this one. And this one, like I told you, is your CH bond. That's your CH bond. Okay. Your syllabus does not really talk about the CH bond as much as that. Okay. Are you see there?
Yes, sir.
Okay, good. So we have done the carbonyl bond 1700 to 1760 wave number, and we have done the alcohol 3,200 to 3,000. This figure must be in your brain. Not, but even though you'll be given in the exam, and then the shape must be in your brain. We have done a shape like this, and we have done the one that's like this. Okay. The next one is carboxylic acids show a broad absorption. So we have done alcohol. Look at it, it's broad. Look at it. And it is not smooth. The alcohol own is smooth, its own is not smooth. So it's broad. Between 3,200 to 3,600, just like the other one. But its own is not smooth. So this is due to the presence of the OH bond as well. But one is smoother than the other. Alcohol is smooth, carboxylic acid is not smooth. They also show a strong absorption at 1,700 cm3 because of the C double bond O there. So this is due to the C double bond O. So whenever you have a C double bond O and then OH, so you have this one will be there and this one will be there. If you see that it's not smooth, your mind should be going to carboxylic acid. See that? So that's how the idea to understand it. One is smooth, the other one is not smooth. Alcohol is smooth, and alcohol does not have the carbonyl functional group. So there won't be no peak at 1,700 to 1,760 wave number. No peak for alcohol. For carboxylic acid, we have a peak at 1,700 to 1,760, and also 23,200 to 3,600. And it's going to be a rough graph. It's going to be rough. Then move on to the next one. S star. Of course, you know the S star does not, it also has C double bond O, O, R. This is S star. The IR is used for functional group identification. So there is C double bond O and then CO. There is a CO bond here. There's a CO bond and also a C double bond O bond here. And there's also CO, this is CH3. We have CO and OC. CO and OC. Anyone? CO or OC, CO. So there's a CO bond and C double bond O bond. Let's look at the ester show a strong absorption at 1,750 to 1,730. Generally, carbonite is 1,700 to 1,760 wave number. General carbonite. For ester alone, the carbonite in ester 1,750 to 1,730 wave number, the CO bond. So you look for that. So that's why you can see that one. And then the ester does not have OH bond. So it will be absent. What you are having here alone now is this one, which is your hyphen CH bond that is there. No OH bond in alcohol, no OH bond in carbonic acid. Does not show. It will only show the carbonite bond of that, which is 17 to 1,730. Okay. Then we'll move on to let's summarize what we have learned today. So in summary of what we have learned today as we end the class, one can tell the difference between alcohol, aldehyde, carbonic acid by comparison of their spectra. And like I said, the alcohol, it is smooth, broad. The aldehyde, as carbonite, just the aldehyde, carbonite, which is ketone and aldehyde. Aldehyde itself, CO stretch, 1700 to 1760. Then we have the carbonic acid that has both OH and then the carbonite stretch, two of them. So when we are having alcohol, you see the smooth one. Carbonic acid is not smooth. It's smooth. For aldehyde, does not have a peak at the OH range like that. Okay. Then let's look at this. So as to summarize, let's look at generally the functional group that we'll be looking at. Remember that between 1,400 to 600 is your fingerprint. So you won't be asked for all of this. So CO bond is out, CCl is out, CC is out, like that. Because they are in the forbidden region, your fingerprint region, you don't go there. But sometimes they may just ask you to identify the CO bond in alcohol or in carbonic acid, CO bond. Sometimes the CCl, but it's very, very rare. What they focus on is this one, then this one, this, the NH bond in amine, OH bond in alcohol and carbonic acid, and then the CH bond, even the CH bond is not a focus at all. It's not a focus. So the carbonite, the aromatic, that's the one in benzene, aromatic. Then we have all of this one. So let's look at it again. Let's look at the alkane. This alkane, this one, this alkane. Look at the frequency relation. It's just 1,600. Just on that 1,000. So it's always a ring. So you will be given your data booklet that they ask to quote. Your data booklet will be given to you in the exam with a question. So look at it. They say which molecule is ethanol or propane or carboxylic acid. They will just show you the molecule. Look at, so you must know what you are looking for. So you hardly look for this one. It's always there. You hardly look for it. But this one is always common. This one is common. This one is common. It's common. It's common, and it's also common. So, very important. The OH bond is very, very important. So this one is very important for both carboxylic acid and alcohol. NH bond for both amine hyphen NH2 primary amine hyphen NHR secondary amine is very important. Okay, they also have absorption like that. Then if that one again, of course, we have done the carbonyl in ketone, aldehyde, alcohol, in ester and carboxylic acid. Okay, let's move forward. So we have here a brief summary of the data booklet. If it is CH bond in alkane, CH bond in alkane, you know alkane is sp3 carbon. You will see the peak at 2,965 to 2,850. Let's go back. Look at it here. This is it. So you can take it down. 2,800. See that? The CH bond. So you see it like this. So between 2,850 to 2,000, maybe 3,000 is there. That is for the CH bond. Okay. Then the CC bond in alkane is, let me go to this one. It's strong. When you see the CH bond is strong. Strong means that how much does it occupy? Look at it. It's occupying about half of the graph. It's strong. Half of the graph. All right. Then we have the CC bond in alkane. Between 1,200 to 1,700 is weak. 1,2 to 1,7. I mean 1,2 to 700. Let's look at it. 1,2 to 1,2 to 700. So we have 1,2 here to around 700. This one, 1,2 to 700, somewhere around this place. So it's weak. Weak is that it's not strong. It's not, the present is not felt. It's not strong. So, but you don't go there. You won't go there because it's the fingerprint region. You don't go to that place. So they won't ask to look for that CC bond. Then we have C double bond, and that's one. Your mind should be in this one. C double bond is alkane, 1,680 to 1,620, like this. It's variable because it depends on the group attached, the group where it's attached to. Because the group that is attached to can delocalize electron, can cause electron delocalization, and so it varies. So there could be electron delocalization. So it is not a constant figure, but you always see it as 1,680 to 620. Then we have ketone, aldehyde, carboxylic acid ester. They come together. So ketone 1725 to 1705. They are always strong, strong, strong. So between 1725, then we also have aldehyde 1740 to 1720, and we have carbolic acid 1725. You always see them. You'll be given this value. You don't cram it, but you must familiarize yourself with them. When we say amide, what do we mean for amide? What do we mean for amide? Amide?
Those with like NH3, NH4, I think.
Okay, like this. Okay, amide should be like hyphen N H C double bond O, like this. That's an amide bond.
Okay.
You find it inside protein or synthetic polymer, like through condensation polymerization, you'll find it there. But it's a compound that is naturally found in protein, amide bond. So the amide bond has the NH bond that will vibrate, and then the CO bond. A CO bond and NH there. Okay, so we have that. So for that amide bond, 1700 to 1630 is also strong. Then we have the CO bond, which is found in alcohol, in ester, in carboxylic acid, and ether. Like I told you, ethers are molecules with oxygen at the center. Ethers are molecules. So we have oxygen like this. So we have C, then we have C. And it's between 1,3 to 1,000. It's strong as well. And it's under the fingerprint region. So you are likely not going to be asked. Then we have the OH alcohol. And we have the OH hydrogen bonded. And we also have the carboxylic acid hydrogen bonded. They have different rates. The ordinary OH that is on alone is hydrogen bonded 3,650 to 3,590. It's sharp. That is like this. It's sharp. Sharp. Okay. Then we have the alcohol hydrogen bonded. It's broader. It's not as sharp. It's strong and it's not as it's broad. It's not like the one that is sharp. Then we have the carbolic acid. It's also broader than the two of them, than both the hydrogen bonded in alcohol and the ordinary one that is not hydrogen bonded. It's broader and it's rough. It's rough. That is 3,300 to 3,200. And you can see that. Look at the frequency reduction, 3,003 to 3,250. The other one, 3,200 to 3,420. So we have the amine and amide. Amine is NH2. Amine is CONH2 hyphen NH2 like this, or hyphen NHR, primary and secondary amine. While amine is hyphen CONH2, primary amide, hyphen CONHR, secondary amide. Okay, so amine, whether that's secondary or primary and what it is, you have them as 3,500 approximately medium of intensity, medium. Then we have the nitrile, 2,260 to 2,240. When we begin to analyze molecules, then you can see. When we begin to look at past questions, then you can see. Then we have the CS bond, that is the alkyl halide. In chloride, in bromide, and in iodide ion, they are always in the fingerprint region. Fingerprint 800 to 600, 600 to 500, and 500. So we see that as going down, the bond length is getting, for the iodide, the CI, the bond length is very long and it's weak. So it has lower absorption, 500. But the chloride, the CCl, is stronger. So we have just 800 and 600. So we have that for that. And then finally, we have come to the end of today's class. And hopefully we will do analysis We'll do examples next week. And I hope you will be able to gain something, gain some idea.
Yes, sir.
So what we will do, it will be, I would look at AS past question and we now will do analysis. So any question?
No.
Okay. Um, this kind of this one and this one. Which one is for alcohol? A, B. Which one is for alcohol?
Um, A.
A or B?
Um, Wait, they're pretty much, they look kind of the same to me. So like, is it possible for you to redraw one and let me see the difference? Because
You will
I
only
guess it's B. It's
okay.
B then.
Okay. The like I told you in the class that alcohol they are not as broad as carboxylic acid. So if you look at it this way, if you look at it this way, this is not as broad as this one is broader. This one is less broader. So this is alcohol. Alcohol. Then let me do another one again so that you will see then. Okay. Um, let me do this one. Okay. So we have A, B. Which one is for carboxylic acid? A or B?
Sorry, B.
Which one is for carboxylic acid? A or B?
I said B.
B. Why?
Wait, yeah, wait. Um,
Okay.
for
Remember I told you.
A1, um, car, wait, I'm confused.
Okay, let me help you. Remember I told you that for carboxylic acid, it is never smooth. The alcohol is very
Yes.
smooth. The alcohol is smooth. It's a smooth curve.
Mm-hmm.
While this one is rough. You can see that it's rough. It's a rough curve. So take note of this one. What is the range of, okay, let us do this one as well. How about this one? One is like this. What kind of, is it, what do you call this one? This one,
Carbonyl.
carbon 9. What is the range
Carb
of absorption?
1,700 to 1,760
Okay, to
wave number.
1,760 wave number. Okay, good. So let's stop here today. So you go through past question, and then next week we'll also go to past question. And we'll first go to examples first and then past question. So that's how it will look like next week. So I know you used to tell me to that I should teach you part 5. So after this topic, which is your IR spec, we also do mass spec. After mass
Mhm.
spec, then we now do part 5. Okay.
Yeah.
But let me
Okay.
know if your exam is closed, then we can start revision. All right.
Okay.
So that's how it will be today.
Thank you.
So I wish you all the best.
Okay.
Bye.
Thank you, sir. Bye.